Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I'm very happy to have Naomi Tsuji with us today. Hey, Naomi.
Hi. Good morning.
For you.
Good afternoon for you.
It is Monday, May 24th. It is roughly about 6 p.m. in Phoenix. And where are you located, Naomi?
I'm in Tokyo.
Tokyo. All right. Very good. Yeah, it's your Tuesday morning then. So,
yeah.
What's your position there in Tokyo?
I'm near Shibuya. Do you know?
Okay.
Central part.
Okay. Very good. I love your background there. What is ITEMS?
This is ITEM. Where I'm from.
Oh, okay. Very good. Got it. Awesome. Very cool. Let's see, you're Northern Hemisphere. So is it summer yet in Japan?
Yeah, almost.
Almost.
It's getting hotter.
Mm-hmm. Mm-hmm. Does it get humid in Japan in the summer? Does the humidity go up in the summer?
Yeah.
Yeah, because you're all around ocean. Yeah, makes sense. But cooling breeze. Very cool. Naomi, what do you like to do for research?
Well, actually, I'm working on observational studies. So I like it because we can actually observe what it is going on there. So yeah, I like it.
And what do you like to observe?
Supernova remnants, I would say.
Okay.
This topic.
And that is going to bring us to this very lovely APJ article on exactly that topic. So we have a systematic study of acceleration efficiency in young supernova remnants with non-thermal X-ray observations. And Naomi, take us away.
Okay, thank you so much. Yeah, I wrote this paper, and well, this is actually a main topic of my PhD thesis. Yeah, what I did is, well, it's literally systematic study of young supernova remnants, and I actually analyzed 11 young supernova remnants, and you can go to table 1. Table 1 lists all the SNRs I analyzed in this paper.
Okay. G1.9, Cas A, Kepler Tycho, G330.2, SN106, 1006, RX telephone number, RCW86, Bailey Jr., Hess J1731, and Supernova 87A.
Yeah, some of them are very famous, like Cassiopeia, Tycho, and some of them are not, I think. But I chose these remnants because they are relatively young, younger than a few thousand years. Yeah, and yeah, they are in our galaxy except 1978A. It's in Large Magellanic Cloud. So, and they are all the distance to those remnants are very well known, and the shock speeds are already measured in these remnants, which is one of the important parameters in this paper. So yeah, I picked up these 11 SNRs. Okay, and then I think we can go to the analysis session. Yeah, section 3 analysis. And the next, the figure in the next page. Yeah, the figure 1. Figure 1 shows the X-ray image of these remnants, yes.
Okay, and these are taken with what instrument?
Mainly Chandra,
okay,
except for RxJ 7013 and yeah, and Virginia. RxJ 7013, the image of RxJ 7013 was taken by XMM Newton.
Okay.
The one of Vera Junior was taken with Suzaku because both two are very large. So, okay. And yeah, you can see the X-ray images.
And so each of them has green boxes
Green
field of view.
Green boxes are the region I defined to extract the spectrum.
Got it.
Yeah, and yeah, the supernova remnant sun, properties are very different across the remnants.
Yeah.
It depends on the region. So I defined these region. Well, actually, I selected the region at the outer rim of the remnants because at the surface of supernova remnants, the shock waves are created, and that is our interest because the particle acceleration takes place there.
Right.
So, for example, well, maybe you're pointing at a Tycho remnant. I defined 20 boxes along the rim, around the outer rim, and actually, in each region, in each 20 boxes, already shock speed was measured. So in each box, I extract the spectrum and fit the spectra and get the cutoff energy. I'll talk about it later. Yes.
Okay, I'm with you. Very good. Okay. Oops. Sorry about that. Okay. Very cool.
Yeah, and I did the same thing for the other SNRs. Okay, and maybe we can go to the spectrum.
Okay.
I think, yeah.
Talk a little bit about the model.
Maybe, yeah. Good point. I think I should talk about the model first. Okay, yeah. Section 303. Yes. Okay, the equation number 1 describes the model. This is synchrotron radiation model from accelerated electrons.
Okay.
And yeah, in the framework of electrons are injected from the shock wave, and they are cooled by synchrotron radiation, and then they diffuse in a bomb diffusion. Well, okay, well, this is the model, and 3 parameters are just normalization and the cutoff energy. Only 2.
Yes.
Yeah, only epsilon 0 is the free parameter, which describes the cutoff energy.
Okay.
Okay, and I used this model, I applied this model to the spectrum in figure 2.
Okay. And we can, got a whole series of them here. So maybe we just want to blow one up and take a look at a few in some detail here. Right. So let's look at G19 plus 03. Okay.
Yeah, okay, the black one is the spectrum taken with Chandra, and the red one is with New Star. So
okay.
With New Star, we can detect a higher energy, so the spectrum is up to 40 kV or so.
Okay.
And yeah, we can get this very nice broadband X-ray spectrum. And yeah, I apply the model in equation 1 and fit this spectrum.
Okay.
Yeah, this spectrum is taken from the east side of this permanency 1.9.
Okay. Ooh, this one's busy. Okay. So each of the lines here is a different box.
the line we actually for Cassiopeia or for some other SNRs, they show some thermal line emission. So I should also add the thermal model and also synchrotron model.
Okay.
So here we have 2 or 3 components. I should account for the thermal model.
Okay.
Yeah, the Cassiopeia, it's in the bottom, the Cassiopeia A, and you see SE, the southeast, it means southeast. And Kepler, this is also the spectrum taken from southeast in Kepler remnants. Well, this looks well easy, right? The upper one shows the synchrotron model, and the bottom one shows the thermal components.
I'm with you. No, no new star on Kepler.
We have, but they are not analyzed yet, and the Kepler is smaller, so with new star, it's the entire remnants are integrated.
Yeah.
I am interested in only small parts in near shock waves, so only Chandra can do this.
That resolution to pick that out.
Yeah.
Yep. Okay, Tycho and G30 and SN106, you got both. Very good. Okay, well, I'll just let you go. Okay, very good.
About the spectrum.
And just one question: do you have to worry about instrument offsets? Like, for example, here in where you have Chandra and New Star, right? You do have an overlapping energy band, and the counts are different at, let's say, the lowest New Star and medium height.
Yeah. Okay. This figure is not corrected for instrumental components. So yeah, you see the difference, but it's actually okay.
Okay, very good. Thank you. Okay. Should we slide on? What would you like to do?
So from with the fitting, we get the cutoff energy. Yeah, you see the equation number 2. Yes. And in the model which I talked before, the cutoff energy depends on the shock velocity and also this eta component. That is so-called Bohm factor and acceleration efficiency. So in this equation 2, you can see if we measure the cutoff energy and shock speed, we can get the eta parameter from this equation, right? That's what I wanted to do.
Okay.
And if we go to table 2.
Example.
Yeah, here I show the results of the spectral fitting in each box in each remnants. Yeah.
Nice.
Of energy and shock speed and the eta component.
Okay.
Yeah, if eta is large, it means the acceleration is not efficient. If eta is 1, the Bohm factor, if it's in the Bohm diffusion, is the acceleration is very efficient. So you can tell if the acceleration is efficient or not in that region by using this eta. Yeah, and I derived eta components in every region. Maybe we can skip this long table.
Let me ask one question here. These the last column over here is an estimate of the magnetic field?
Yeah, magnetic field, which So we apply the model in equation number 1. And for the
What would
for
be?
the condition is fulfilled, the magnetic field should be larger than these values. So if
Okay.
magnetic field is larger than these, for example, 39 microgauss in the G 1.9, and
Okay.
then we can use apply the model.
Got it.
So, well, the magnetic field is about 20 or 40 microgauss.
Yeah. Yeah.
I believe they are reasonable. The magnetic field might be higher than these values, and so that we can apply the model.
Wow, this is fantastically detailed.
Yes.
And there's our Bohm factor that we were just talking about, eta. Yeah,
Okay,
you
yeah.
converted that to get eta.
Yes.
Uh-huh.
Cool.
Okay.
Okay, and then figure 3. Okay. And here I show the relation between the cutoff energy and shock speed, which I derived in the last section.
Okay, let me zoom in on this one a little bit. Okay, shock
This
speed
one,
at epsilon 0. Okay.
yeah. And here I show the plots from all SNRs. And yeah, as I defined some regions in each SNR, I just picked the maximum epsilon 0 region in this plot. So you can see many variety, right? Shock speeds are very different and cutoff energies are very different from SNR to SNR.
Indeed. And what are these green lines? Oh, these are
Green
different.
lines is, yeah, the model, the equation number 2 or 3.
Okay.
The solid one indicates eta is 1. So that is the most efficient acceleration here. And if it goes bottom right, it becomes inefficient.
Okay. So that's for all. And then we walk through a couple of individual ones that have like lots of boxes, like Kepler or Tycho.
We can go to, Kepler or Tycho first.
Okay.
Kepler or Tycho. Yeah, for example, Tycho, like I said, I defined 20 boxes along the outer ring. And yeah, as I talked before, some regions include thermal components. And sometimes the thermal components dominates the non-thermal, dominates the synchrotron radiation. Okay. And I just showed the results which the synchrotron radiation is dominated in black plots. And okay. In gray one shows the region where thermal component is dominated. So I'm interested in the non-thermal components, so maybe we can take a look at the black plots. And if we, for example, take a look at Kepler one, region 4, 5, 7, 8, 6, they are well described by the dashed line, dashed curve, and that means dashed curve is
that was an eta.
Eta was 3. Yeah, eta was 3. For it's same for Tycho. Tycho is also the relation between epsilon 0 and shock speed are very well described by the model with eta of 3. So for these two remnants, we can say like standard acceleration is going on.
Okay.
Yeah, but it's not that easy for the other remnants.
Okay.
Take a look at, okay.
Let's look at 6.
And then 6, yeah.
That's a little all over the place.
Right? Yeah, a little bit like opposite trend. The shock speeds are are not so different from region to region, but the cutoff energy is very different, and we can't reproduce these results with one theoretical model. Okay.
Interesting. Okay.
And so, for example, SN1006, we want to understand what is going on here, and maybe we can go to the next page, results, and I present a short explanation of each SNRs, and you can maybe read if you're interested in it.
Okay, yep. There's a discussion of each of them, whether it fits one model or what's going on. Very good. And
okay.
So here's 1006 again, eta variation.
Okay, maybe we can go to the next session. Here I show, I just showed, I just wanted to say there are many varieties of acceleration in supernova remnants, and we can't, it is difficult to understand in a single simple model.
Mm-hmm.
In the next session, in figure 5,
okay.
I think we can skip the figure 4 and go to figure 5.
That's
yeah
fine.
Here
Okay.
I show not individual SNR, but the eta derived from all SNRs, and I showed the eta value as a function of the age. So you can see sort of evolution of its acceleration efficiency.
Okay. What is the difference between the black numbers and the red numbers?
Well, for example, number 1 is the one of Z1.9, and I defined 4 regions. So if we take, if I pick up the region with maximum cutoff energy, it is in the black plot. But
Okay.
if I take the average value of all the region, and then it goes for red one.
Got it. Got it.
Yeah, okay. Then I see in this figure, if the remnant scaling older, and then eta becomes smaller.
Yeah.
We can see this kind of evolution. And I fit this plot with empirical model with.
So if I say this in words, this means that the older it gets, the less efficient it gets.
It's more efficient. If it
more
is
efficient, correct.
Small, if it is small, it means
1 over. Okay, so the older it gets, the more efficient it gets, right?
Yeah.
Okay, very good. And then we got.
Right one show actually the same plot, but the x-axis is expansion parameter of SNR.
Yeah, M here was a power on the radius.
Yeah.
Expansion parameter.
So M is 1. It is the start of explosion, and if M is 0.4, and it's a set of phase.
Yes. Good.
So here we also see the evolution. It's not so clear as the one before, but okay. And we fit the plot.
Sorry, and what is the average values of the red dash line? Okay, good. I'm with you. I got it.
And this the model shows the model is describing figure equation 7.
Okay. Oh, there's our 8. There we go. There we are. And there's our M. Yes. Okay.
Yes, yeah, as we saw, yeah, fit the plot with this model, and it depends on the age. Okay. Yeah, that means yeah, if it gets older, the exertion efficiency becomes good.
Yes.
And well, this is yeah, this is because what we think is if it gets older and more particles are accelerated,
Yes.
and then the accelerated particles themselves can create magnetic field turbulence. And if the magnetic field becomes more turbulent, and then the particles can be accelerated more efficiently because the particles scatter with magnetic field turbulence. And if we have more turbulence, and then it's easy for particles to be scattered and accelerated. That's
Okay.
what I think. Yeah, it is.
Good.
And that's the main point of this paper, the evolution of exertion efficiency.
There's the money plot. Okay.
Yes. Okay. And then maybe, yeah, figure 6. The figure 6,
Split by type.
yeah, I showed the same plot, but with 2 groups, type 1 in top and type 2 in the bottom.
There we go.
Yeah, and here we can see a slight difference. For example, well, type 1 tend to show a larger eta, and for type 2, it's a little bit smaller. And I did the same thing with the plots, and yeah. Yeah, unfortunately, this difference is not so significant now.
Now, right, we'll get to that.
I think, yeah, it might be interesting if these 2 types remnants show the difference. So maybe this is the future work. Maybe we can make the LR bar smaller, and if we have more samples, then maybe we can yeah, say something robust in the future.
It's a good opening. It's a good opening shot at it. Very nice. Very good. Okay.
Okay, that's, yeah, almost 8.
Okay.
Figure 7. Yeah, and yeah, in table 3, I show all the fitting parameters.
Pearson. Oh, that's your Pearson. Okay. Row here is your Pearson correlation.
Yeah.
Okay. Okay. Good.
Good.
Those are the 2. Okay, I'm with you. Okay. And figure 7.
Okay, in the figure 7, I plot again the relation between cutoff energy and shock speed with from these 5 remnants. The same color showed the same plots from the same remnants and with different regions.
Okay.
If we plot, if I show all the plots in one figure, you can see very variety, right?
Yes.
Yeah, so like I said, Tycho and Kepler, they can reproduce by the green theoretical models, but for the other Cassiopeia or SN10 61.9, they're not follow the theoretical model. Maybe we have other reason. Well, okay, good. Yeah, and yes, the section 5.2, equation 11. Yeah, like I said before, the eta also depends on the magnetic field turbulence, and this the right term show the level of magnetic field. B 0 is initial background magnetic field, and delta B is the component of turbulence magnetic field. And as SNR is getting older, and we see the eta component becomes smaller, and that means this delta B, the turbulent magnetic field, becomes large. So many more and more magnetic field turbulence are formed, probably because of the X-rated particles themselves. And
Right.
then we think, yeah, this can explain what we observe. Okay, I think, yeah, I talked about, okay, finally I can just comment of the maximum attainable energy in the next page, I think. Page 14, section 5 to 1. Yes. Yes. The equation number 3 describes the maximum energy of protons. This time I'm talking about the protons. And yeah, the maximum energy of accelerated protons depends on some parameters, as you see in equation number 3. The time and shock speed, magnetic field strength, and eta parameters. So before, we believed that these eta components might be constant with no reason. We just assumed that this eta is constant.
Okay.
But with in this work, I show that eta might depend on time. So we should take account for that time aberration as well. And yeah, these other shock speed or magnetic fields also depend on time. And I also show in figure equation 16.
Yes.
Yeah, in the below equation number 16. Yeah, I also account for the evolution of eta. And then it goes to equation number 17.
Yes.
The maximum energy of accelerated protons depends on, yeah, in that way. And this delta component is from the evolution of eta. So if we consider this evolution of eta, maximum energy of protons can be higher than we believed before. So that's, I think it's interesting. So if we consider the time dependence on eta, so we probably can get the higher energy of protons. And maybe good news because we believe that the cosmic rays below me are produced in supernova remnants. But one of the problems is we do not see any Pevatron so far.
So far, yes. Widely expected, not seen yet.
True. Yeah.
Yeah, very good.
Okay, that's it, I think. Yeah.
Very cool. Very cool. And we do some summary, and then we got a very large sets of appendices on details of the logs of the observations. Very cool.
Yeah, they are observed many times. So
They're all stored for antiquity. Naomi, that was great. Thank you very much for walking us through your really lovely paper. And let me ask you, and you hinted about it a few times, right? Where do we go from here in the future? Are there new telescopes coming up that will be able to provide additional data, let's say as a function of supernova type? Or are there different models to consider that may be able to cover the ones that were not covered by the model that was shown? So just kind of where do we go from here over the next, let's say, 5 years?
okay, yeah. Previously, I just said we believe that SNRs are Pevatron candidate, but actually we do not see any signs yet. But now actually in China, there are these new types of telescope of high energy TV gamma ray telescope, LARSO and Tibet, and they found some Pevatrons from some SNRs. So yeah, they just find them. So maybe there are lots of work to do. But I think with the new telescopes and also the CTA, the Gamma Ray Telescope Array is also coming, and we can also explore more much details about the TV gamma ray of SNRs. And also, yeah, in the X-ray studies, the Chandra has the best angular resolution, and we also have NuSTAR to cover the high energy X-ray bands. But the NuSTAR's angular resolution is not as good as the one with Chandra. So in the future, I hope we should launch hard X-ray telescope with better angular resolution. And yeah, I hope, yeah.
Does Japan have any plans on building such a telescope?
Yeah, it is called FORCE.
Oh, okay.
For hard X-ray telescopes.
Cool.
But it's project, so we're not sure.
Sure. It's still in the proposal stage. Okay. Well, keep my fingers crossed for it and hope that works out. Very nice. All right, Naomi, thank you again very much for sharing your article and your thoughts in the future. And thank you, everyone, and we will see you on the next one. Bye-bye.